All right, I'm looking forward to it. I like this chapter a lot. Okie doke, chemistry 3111. We left off last class. We looked at the first few reactions in the chapter, and the last one that we looked at was a nitration reaction. And so if we go all the way down to the end of the chapter and we look at all the reactions that we covered, let's just rehash this, okay? We covered bromination, then that's reaction one. Then we covered reaction two, which is chlorination. The one that you just saw on that slide was nitration. With nitric acid and sulfuric acid, you make a nitronium ion. The next one was the formation of a sulfonic acid using fuming sulfuric acid. And of course, you can remove a sulfonic acid using dilute sulfuric acid. So it's not written, oh yeah, it is. It's written right here. So dilute sulfuric acid will remove that. What else did we talk about? We talked about we've talked about benzylic bromination. That would be this reaction down here. If you have a benzylic proton, you treat that with NBS. You can replace one of those protons with a bromine. And what they're showing you here in this reaction is if you use excess NBS, you can replace every benzylic proton with a bromine. So we covered that. And then we also covered the reduction. So that would be this reaction here, the reduction of a nitro group using zinc and HCl or iron and HCl followed up by sodium hydroxide to make an aniline derivative. And so what we're going to start off with today are going to be these two reactions. I'll use my yellow highlighter. This first one here, this is called Friedel-Crafts alkylation because we're installing an alkyl group. And this reaction here is called Friedel-Crafts acylation because we're installing an acyl group. When you have a carbonyl on the first carbon, we call that an acyl group. So alkylation and acylation, and you can see that we're going to do things with those products as well. We're going to do oxidations and then reductions. So we'll get into that too. But Friedel-Crafts alkylation and Friedel-Crafts acylation is going to be kind of the focus of the first part of the lecture here today. And it's actually a pretty lengthy section. And I'm not saying that to intimidate you or anything. That's just, the truth of it. So let me find, where did it start? Somewhere around here. So again, the last thing we covered was nitration. And now we're into Friedel-Crafts alkylation. So what I think I'll do is go through these reactions, alkylation and acylation. Then we'll go back to that slide with all the reactions and kind of do a little review of them all. All right, so alkyl. What is an alkyl group? An alkyl group is any kind of hydrocarbon group, right? Could be a methyl, a butyl, tert-butyl, etc. Right? When we talk about alkyl groups, oftentimes we just replace them with R, right? An R group, the remainder of a molecule. And so if we want to alkylate or install an alkyl group on an aromatic ring, what do we need? It says we need an alkyl halide as the electrophile and aluminum chloride as the Lewis catalyst. Right? If you just look at this molecule right here, if you just look at 2-chlorobutane, is this molecule an electrophile on its own? Absolutely it is. Yes, there's no arguing, right? We have a dipole going this way, and so this carbon is delta plus, and you can imagine that working in an SN2 or something, or reacting in an SN2. Okay, but that's not what we're doing here, right? Because we know that an aromatic ring, like benzene, this is not a powerful enough nucleophile to just attack the electrophilic carbon here. We have to spruce up the reaction conditions with this Lewis acid catalyst, aluminum chloride. And when we do that, what we see is that we form a bond between our aromatic ring and the alpha carbon, the carbon attached directly to the chlorine. So again, we need our aromatic ring, of course, our benzene. We need our electrophile, our 2-chlorobutane in this case. And then you need a Lewis acid catalyst, right? You need a Lewis acid catalyst. And in this case, they're using aluminum trichloride. And you can see that the yield of this reaction isn't that bad. Well, if there's one thing that you need to know from this chapter in terms of mechanisms that you've probably recognized already, it's the mechanism of electrophilic aromatic substitution. Right? We saw the mechanism for nitration, sulfonation, bromination, chlorination, and we saw that they were all pretty much identical, and there's going to be very few exceptions throughout this chapter. So if we look at the reaction between the alkyl halide and our Lewis acid, we see that the chlorine dumps electron density, right? It acts as a Lewis base. It dumps electron density into our aluminum atom on our aluminum chloride, which is our Lewis acid. And then we end up breaking this intermediate apart and getting a carbocation, right? We end up with a secondary carbocation. Now that is a very, very powerful electrophile, so powerful that if you put it in the presence, okay, and there's your secondary carbocation, if you put it in the presence of an aromatic ring, the aromatic ring is going to react, right? So it's the same old thing. Again, this is our mechanism of electrophilic aromatic substitution, except this is just used in a Friedel-Crafts alkylation. So we have our nucleophilic attack by our aromatic ring. We make our sigma complex. You should always be able to draw all of the resonance contributors to the sigma complex. And then the last step is always that proton transfer, right? And just like we saw with chlorination, we end up breaking the bond between the chlorine and the aluminum on the AlCl4 minus ion, and we end up making not only our, so this would installing our alkyl group here, but we also end up with HCl, and we recycle our Lewis acid catalyst. There you go. So that's Friedel-Crafts alkylation, installing an alkyl group. Now, if you look at this carbocation, can anybody tell me, how would you characterize this carbocation? Would that be primary, secondary, tertiary? What do you got for me? What kind of carbocation is that? Absolutely. My students are all saying secondary, right? This is a secondary carbocation. And they're drawing that secondary carbocation unto itself there, and they're showing it being attacked by the aromatic ring. But if you're, really sharp on your carbocations, you're probably thinking, well, you can't do that with a primary or a methyl carbocation because they're way too unstable, and you would be 100% correct in assuming that. And so that's going to change our mechanism slightly. Let's take a look. If you wanted to use a primary alkyl halide, like here we have ethyl, right? This is ethyl chloride, and we have our aluminum trichloride as our Lewis acid catalyst, same as always. Well, now we're never going to make this. Okay, don't even draw this. This is a heresy, right? You're never going to make a primary carbocation like that. In fact, I'm going to put a big scarlet X over it like that. So what's going to happen is that the electrophile, in this case, is presumed to be a complex between the ethyl and the ethyl chloride and the aluminum trichloride. So this is what our electrophile is in this case. And so our aromatic ring is going to react with that. Now, if we go back here, something I neglected to say, this is specifically an ethyl group, okay? There's no way that this could rearrange to give you anything but an ethyl group being installed because there's only 2 carbons in it. But what if I had something like N-butyl chloride, right? So this is, or you could call this 1-chloro butane. Okay, it doesn't matter. Both names are correct. N-butyl chloride, they mean the same thing. Anyhow, so if we think about this, this is a primary alkyl halide, right? Primary alkyl halide. And so what's this going to do? When it forms the complex with the Lewis acid, okay, that you have shown here, it can undergo a hydride shift. Okay, it undergoes a hydride shift to give you a secondary carbocation. And so what you end up with, whenever you have a primary carbocation, you end up with installation of the aryl group at that primary carbon, okay, this carbon here, but you also end up with installation, maybe I should label it here, with the product of rearrangement as well. And you can see that the product of rearrangement was actually obtained in a higher yield than that that occurred without rearrangement. So again, if you have a primary alkyl halide like this, you're going to have some rearrangement. So you're going to get nucleophilic attack on this carbon or substitution, and you're going to get substitution on another carbon as a result of a rearrangement as well. All right, or a hydride shift. So let's take a look here. These are things that you just need to memorize. So I'm going to put this in red letters here. Memorize these Friedel-Crafts limitations. Okay, if you remember the character Dirty Harry Callahan, right? He said a man's got to know his limitations. Well, you need to know the Friedel-Crafts limitations, right? So anyhow, what are the Friedel-Crafts limitations? There's 3 of them that everybody needs to know. You'll need to know them for the quiz. For the final exam, they're kind of, I guess you'll kind of have them down pat by then. So yeah, there's 3 limitations. Number 1 is that halogen on the electrophile, it's got to be attached to an sp3 hybridized carbon. If it's on an sp2 carbon, nothing happens. Okay, so that's pretty quick to remember. sp2, chloride, bromide, no reaction. Okay, it just doesn't work. You get zilch. Okay, that's the first one. The second one is if you try to do an alkylation, right? Here, there's trying to install a tert butyl group. You usually get polyalkylation So that means you just get more than one group substituted. I'm going to make a note here for us, though, since we're learning this subject. In Chem, the pencil, the 3101, we will assume mono calculation. Okay, so don't stress about this and think, oh, good gravy, does Mr. Dion expect me to know, is this going to add 2 times, 3 times, whatever? In this class, come on, we're learning the subject. Let's just assume it adds once, okay? So we'll install the group once, all right? Another one, though, this is an important one for you guys, is it says some substituted aromatic rings like nitrobenzene are just too deactivated to react. So what that means is that since a nitro group is so electron withdrawing, there's a dipole going this way that's so strong that this can never act as a nucleophile. It just won't react. Those electrons are not leaving that ring. They're like, hello, I'm not going to go and attack some bozo alkyl halide. Not doing it. Okay, so super deactivated. And I've had students, who are always, a few steps ahead, have asked me, do you have a summary of all the deactivating groups and activating groups? We're going to get to that. It's going to take us a while, but if you want to know ahead of time, if you just can't wait, it's table 18.1. Table 18.1. It covers all the activating groups and all the deactivating groups, and of course, it's my job. I'm going to go over every single one of them with you. All right. So, oh boy, it's a Friday afternoon. Let's get started with trying a little problem here. It says predict the expected products when benzene is treated with each of the following alkyl halides in the presence of our Lewis acid, aluminum chloride. In each case, assume conditions have been controlled to favor monoalkylation. Okay, again, like I said, that's an assumption you can always make in our class. Okay, I don't expect you to be some kind of world's renowned expert on Friedel-Crafts of every alkyl halide under the sun. No, that's not realistic. So let's take a look at A. We have our aromatic ring, right? And we're going to react that with cyclopropyl chloride or chlorocyclopropane. Or did I say cyclopropane when I meant cyclohexane? There we go. Cyclohexyl chloride or chlorocyclohexane. My mistake. And aluminum chloride. And all we're going to do is we're going to substitute a hydrogen, right? We're going to substitute one hydrogen for the cyclohexane group. So we end up with something that looks like this, right? So we end up with a little something that looks like that. There you go. What do you think? Not too bad? Everybody get that one? Yeah? All right. Okay, well, let's try the next one. Tiana, what about the next one? This one here, you got tert-butyl chloride. If I take my aromatic ring, okay, and I treat it with tert-butyl chloride, so we'll put here tert-butyl chloride is this molecule. There we go. And my Lewis acid catalyst. Is that going to undergo any kind of rearrangement? And it's not, I'm not trying to fool you. Go with your gut on this one. Exactly. I can't rearrange, right? You can imagine that if it was a tert-butyl carbocation, that's not going to rearrange under any circumstances whatsoever. So just scratch that, right? It's not going to do it, right? That's my George Bush Sr. impression. There we go. All right, so we're going to put our tert-butyl group out here. And then for the last one, it's a primary alkyl halide. So we have to look out here, right? Now, there's no such thing as a primary carbocation, but if we imagine one, let me just draw an imaginary one here. We can imagine that if you formed the primary carbocation, right, at this carbon, that could undergo a hydride shift, couldn't it? Right, because you've got a hydrogen here, and that would undergo a hydride shift like this. And then what would that give you? That would give you this, right? That would give you, you'd go from a primary to a tertiary carbocation, right, where we have the positive charge over here. So the answer is it's going to do an alkylation at both the yellow carbon and the green carbon, right? Both are a possibility. Now, if you want some mechanistic information on this, we could practice drawing the mechanism and just say, let's just put in some lone pairs here, put our aluminum chloride here, and what's going to happen is this going to dump its electron density in here like this, and then we end up with this guy. So we end up with something that looks like this. I'll draw that proton in again. So we end up with the chlorine here, and of course it's got a positive charge, and it's attached to the aluminum, which has a negative charge. And then what's going to happen is it's going to undergo a rearrangement, right, where you move the proton over here, and then you're going to put this pair of electrons on the chlorine like that. Okay, so you're going to undergo this rearrangement so that you would end up with, again, this tertiary carbocation. So again, it's going to alkylate at both positions. All right, both positions. But here it's saying, it's going to favor monoalkylation. So I could have drawn the product showing it alkylating at the yellow carbon and the green carbon. But if you go back to the example that we looked at before, okay, what we presumed is that the rearranged product was the major product, okay, the one that comes from the hydride shift. And so that's what we're going to do, Tiana. We're just going to draw one product. Since I'm getting ahead of myself, aren't I? Since it said monoalkylation, let's just draw that one product. So we're going to have our aromatic ring, right? And we're going to take it and treat it with this alkyl chloride. And oops, I'm missing a carbon here, aren't I? There we go. That's a little better. There we go. And so we're going to end up with this as being our major product, right? So we're going to have two methyl groups on here, and then we'll have 1, 2. Let me fix that. 1, 2. There you go. So that's going to be our major product. Again, what I'm doing is I'm adding to this. Where's my green highlighter? To this carbon right here. All right. Give me a thumbs up if you follow me on that last one. It's a little trickier than the other ones, okay? So B can't rearrange because it would give you a tertiary carbocation, right? You can't have a tertiary carbocation rearranging. All right. Does that make sense, Michelle? Right. Remember I drew this a few minutes ago? I drew this. If you have a tertiary carbocation like that, that cannot undergo any kind of rearrangement. All right. There we go. Well, good. Let's move on to acylation. So remember those little, let's back up. We got time. Just remember those little nuances. So again, let's review. Your alkyl, your chloride has to be an alkyl chloride, right? It can't, you have to have an sp3 hybridized carbon attached to the chlorine or bromine, okay? Can't be sp2. The other one is polyalkylation can happen, but we're not going to assume that. We're going to assume monoalkylation. And the last one is if you have a really deactivating group, Friedel Crafts doesn't work, okay? And we'll see some examples of that later on. We tried some examples here. So let's move on from alkylation to acylation. And like I tried to tell you at the beginning of the lecture today, if we just have a regular old R group, that's what we call an alkyl group. But if we have a carbonyl followed by an alkyl group, then we don't call it an alkyl group, we call it an acyl group, okay? And if you remember studying acetyl coenzyme A in biology class, an acetyl group would be a type of acyl group, right? An acetyl group is when the R group is a methyl. Okay, so if you have this is called an acetyl group, okay? If the R group is a methyl. I'll just put that bug in your ear because I know many of you have studied biology and probably even advanced biology classes at this point. All right, so acylation reactions, we also need a catalyst, right? A Lewis acid catalyst, same old one, aluminum chloride. If you keep wondering, like, hey, Mr. Dion, I studied General Chemistry 1 and General Chemistry 2, and I remember seeing other Lewis acids than aluminum chloride. Why is this so popular? Probably because it works well, would be number one. But number two, aluminum chloride is just a white solid. It's very easy to mass on the balance. It is hygroscopic, meaning that it does absorb water from the air kind of quickly. But it's, as far as compounds to work with, it's not that difficult to work with aluminum chloride. So that's why it's a real fan favorite, if you will. Anyhow, let's take a look at an interesting reaction, the reaction between an acid chloride and our Lewis acid, right? Because when we do an acylation reaction, we use a Lewis acid, right? So this is our Lewis acid. But if you don't remember this functional group here, this is what we call an acid or an acyl chloride. So either one works. I'm going to call it an acid chloride here. Okay, it's just like a carboxylic acid. You just replace the hydroxyl with a chlorine and you get an acid chloride. Okay, so let's take a look at the reaction between the acid chloride or acyl chloride, either way. So acid chloride, and this is our Lewis acid. So we have the Lewis base reacting with the Lewis acid. we form the complex. So this is our complex here. And then the complex undergoes a degradation, or it breaks this bond between the carbon and the chlorine to give you the aluminum tetrachloride ion and an acylium ion. And if you look really closely at this acylium ion, if you're very astute, and I know you all are, you're probably recognizing something interesting about this, which is going to prevent the acylium ion from rearranging, right? No rearrangements. This is not going to rearrange under any circumstances. Why would that be? Let's take a look at the next slide. The reason why it doesn't rearrange is because it's resonance stabilized. And in the second resonance contributor, look at this. Everybody's got a complete octet, even the carbon, okay? So that is why the acylium ion doesn't undergo any kind of rearrangements whatsoever. It just acts as a really great electrophile. So there you go. So that actually simplifies acylation a little bit, and it gives it even more synthetic utility than you might have thought. So let's take a look at a reaction between our aromatic ring and the acylium ion. I mean, if you're having trouble straightening all this stuff out in your mind, you know how we've looked at like maybe six mechanisms that have kind of followed this pattern so far? They all follow the same pattern, right? The idea is that you put an aromatic ring in the presence of a very strong electrophile. On this slide, it's the acylium ion. On the previous reaction, the Friedel-Crafts alkylation, it was a carbocation or a complex, okay? On the sulfonation, it was sulfur trioxide. On the nitration, it was nitronium, right? In the chlorination, in the bromination, it was a very electrophilic source of chlorine or bromine, right? It's the same pattern every time. We get our nucleophilic attack by our aromatic ring onto our strong electrophile, and we make our sigma complex, right? And you've got to be able to draw all the resonance contributors of the sigma complex. Last step in all of these is a proton transfer, and you end up installing your acyl group. And there you have it, my friends. That's it. Now, we're missing two things here. So you'd also get you'd also get HCl and aluminum trichloride at the same time, right? You'd get all three of these things at the end of the reaction. So there you go, Friedel-Crafts acylation. Now, when would you want to use an acylation? Let me give you a really good reason. What if you wanted to install a butyl group like this? I just showed you a few slides ago that this reaction will not work. If you took an aromatic ring, okay, like a benzene ring, and you treated it with this compound, 1-chlorobutane and aluminum trichloride, you are not going to get the compound that we have shown here. 1, 2, 3, 4. You are not going to get this compound, right? It's going to mostly give you a rearrangement where you're going to get this compound. Okay, I shouldn't even put plus because you're mostly going to get this guy here. You're going to get sec-butyl, right? Because it's going to rearrange via a hydride shift, and the alkylation will occur on this carbon. And so the utility of the acylation is, check this out. If you were to treat this with the aromatic ring with this acid chloride, okay, you install your acyl group, and that's all well and good. But if you want to convert that from an acyl group and you want to remove that carbonyl or convert that to a CH2, you can. The way we do that is using a reduction. This is called the Clemmensen reduction. Okay, where we treat the carbonyl, so in this case it's a ketone, with zinc and mercury in brackets. So I'll get to that in a second, and then HCl and heat. So if you're wondering what zinc, I don't know if I have it written here. No, I don't. Okay, so where it says zinc with mercury in brackets, that's called a zinc mercury amalgam. Okay, and it's a mixture of the two. It's like zinc with a mercury on the surface of it, essentially. I'm not going to quiz you on that or anything, but you use the zinc mercury amalgam and HCl and heat, and it just makes the oxygen go away, and it replaces the oxygen with 2 bonds to hydrogen. Okay, so we just burn that off and we replace it with 2 hydrogens. So it's a reduction reaction, isn't it? All right, so this is a very useful way of installing an alkyl group, a primary alkyl group, onto an aromatic ring. Well, let's take a look here. It says polyacylation is generally not observed, which is a problem, as we saw with alkylation. The reason why it doesn't happen is because once you install the acyl group, this is deactivating. It pulls electrons away from the ring, and so it renders the ring a really weak nucleophile. It becomes a really crappy nucleophile, so you can kind of remember that. But again, in this class, we're always going to assume monoalkylation and acylation anyway, right? That's what I told you. So let's see here. This question requires some thinking. I'm going to put on your thinking cap for this one. Identify whether each of the following compounds can be made using a direct Friedel-Crafts alkylation or whether it is necessary to perform an acylation followed by a Clemmensen reduction to avoid carbocation rearrangements. So if we look at the first one and we think of it in terms of a retrosynthesis, right? We have our aromatic ring, of course, right? So that's not going to change. And then our alkyl halide would be all of this, okay? All of that. And then, of course, we would have I'll put a chlorine on here, okay? So my question is to you, is this going to undergo any kind of rearrangement? Yes or no? Right? Will this undergo a rearrangement? I would say, yeah, wouldn't it, Tiana, right? Because if you were to have, right, if you were to think of this primary, right, carbocation like this, oops, I'm missing a methyl group here. There we go. That's going to undergo a methyl shift, isn't it? It's going to undergo a methyl shift like this to give us something that looks like this. So then we end up with a tertiary carbocation, right? So this would be methyl shift. And so we can't just do it by Friedel-Crafts alkylation. We're going to have to use acylation is what we're going to have to do. Okay, so we'll write down here, must use acylation. And so what's that going to look like? I'll write the whole scheme down here. So we're going to take our aromatic ring and we're going to react it with the acid chloride that we need. So yeah, there we go. Make sure I have everything in the right place. We need our Lewis acid, and that's going to give us the acyl, the acylation product, which is going to be this. All right, like so. And then we're going to reduce that carbonyl using the zinc mercury amalgam. We need HCl, and we need to heat that up, and that's going to give us the desired product. It's going to look just like that. Okay, we got another one to try here. We're gonna have to try it on a blank space here. So I'm gonna go over and grab some more Taylor Swift blank space. So just bear with me here. Let's see, do I have any, oops, that's the wrong thing. Do I have any space on any of these? I love using up my blank space. Come on. No? Okay, I got one little bit of room here at the end. So let's think about this problem. Again, this is question 18.8 from Klein, 4th edition, so 18.8, and it is question B. Okay, so let's see here. We had this product, or this compound is what we wanted to make. And the question was, could you make this directly via a Friedel-Crafts? So that would mean you have your benzene ring, and then you would need this alkyl halide. What do you say, yes or no? Could you use alkylation here? Yes or no? In this case. It's a big no, isn't it? Thanks, Tiana. Thanks, Maria. Thanks, Michelle. No, absolutely not, right? We're going to have to use acylation, right? And if you were wondering, well, why do they all know that it's a big no-no, right? Because if you had this as your alkyl halide, right, you would think of that as being primary, right, like this. Maybe we could pretty that up a little bit here. And what's going to happen is that's going to undergo a hydride shift, right? And that would give you like a terbutyl carbocation like that. Okay, so it's not going to alkylate at the right carbon. It's going to undergo a rearrangement, and you would actually end up with terbutyl. Right, you'd end up with terbutyl benzene is what you would get, right? If you use that as your reagent. And so we need to do an acylation followed by a Clemmensen reduction. So let's write the whole thing down. We have our benzene. That's going to react with our acyl or acid chloride like this in aluminum chloride. So we install our acyl group like this. And then we do the Clemmensen reaction, which is zinc with a mercury amalgam in HCl. And we heat that up, and that's going to give us the desired product. I should point out that there's no mechanism whatsoever for the Clemmensen reduction in our textbook, okay? So no Clemmensen reduction mechanism. There isn't one in our textbook, so you don't need to know it. So let's go back to our slides of chapter 18. Let's go all the way back down to the bottom now that we've covered Friedel-Crafts alkylation and acylation. So just bear with me here for one memento here. So select all. Let's just delete all this. Okay, so what have we covered this so far? We have covered bromination. We've covered chlorination. We've covered nitration. We've covered sulfonation. We've covered desulfonation. You need to know the mechanisms of all of these, even the desulfonation, because it's the reverse of sulfonation. I've never asked it on a quiz or anything like that, but there is a question in the textbook that asks about it, so I think it's a good idea to give it a shot. You need to know Friedel-Crafts alkylation and acylation. We also looked at the reduction of a nitro group to an amine, right? So we covered that in detail, so you need to know this reaction. There's no mechanism for that reaction, no mechanism covered. Then we looked at, what else? We looked at the Clemmensen reduction. So Clemmensen reduction would be this reaction here. And keep in mind, there's no mechanism for that reaction. So the ones you need to know the mechanisms for that we've done so far would be this one, this one, this one, this one, this one, and this one. But again, it's always the same mechanism every time. And then there is one other reaction that we covered, and that was benzylic bromination. And we're going to look at that even more later on. But there you go. That's quite a bit of chemistry that we've covered already. So let's keep going. Let's keep going from there. And if you're wondering, well, come on, why are there so many more slides if we've covered the vast majority? Well, remember that there are other sections that we haven't covered yet. And what we need to really focus on is taking all these reactions and using them to make something useful, right? We want to be able to apply them to a synthesis. We also need to ask ourselves the question, okay, well, how is electrophilic aromatic substitution going to proceed if I have some kind of group on my aromatic ring already, right? What are we going to do then? Okay, and that's going to be the focus of the next section. So let me show you what I mean if you're not following here. What I mean is something like this, okay? What if we have a methyl group on our aromatic ring? What if we have a toluene and we want to do a nitration? Where is the nitro group going to go? Is it going to go in the ortho, in the meta, or the para position? Right, and that's, again, what we're going to cover in the next few sections, actually. So there's two questions that we want to ask here, okay? Number one is, what's the effect of the rate? So is the reaction going to be faster or slower now that we have this methyl group there? And it actually turns out that the methyl group reacts a lot faster than benzene, okay? It reacts about 25 times faster than benzene. Now, I'm not going to quiz you on that, but the idea is that you should know that it does react faster. And the reason why it reacts faster when you have the methyl group on here is because the methyl group is electron donating via hyperconjugation. And so it makes the ring a better nucleophile, right? It wants to be a better nucleophile. It's more prone to donating electrons. And so there's the first part. The second part is the one that we're going to focus on way more. Okay, this is going to be way, 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 way more important than rate to you. Is what's the effect of the methyl group on regioselectivity? Like I said, are you going to get the ortho product? Are you going to get the meta product? Or are you going to get the para product? Which one is it going to be? Again, are you going to be in the para position? Are you going to be in the meta position? Or is it going to nitrate in the ortho position, right? And it really depends on the group you have where you're going to get your substitution occurring. So let's take a look here. This is an experiment that's been done many times. And what happens when you take toluene, so remember this is toluene, and when you nitrate that, you actually get a mixture. You can see that it's mostly ortho and some para and almost none of the meta. But the majority is ortho and para nitrotoluene, and we get a little bit of meta nitrotoluene. Now, why is that? Okay, there's got to be some kind of reason for that. I bet you that you guys could probably guess one of the reasons. One of the reasons is that, there's more ortho places than there are para, right? There's twice as many ortho, so maybe that's why there's more para, right? But that doesn't hold that much weight because there's twice as many metas as there are paras, and you don't get very much of that. So maybe that's not a very good argument. So what is it really? Well, do you guys remember the sigma complex, right? The carbocation that you could draw all these different resonance forms of. The key to all of this that we're going to talk about for probably the next hour is going to be in the sigma complexes. So that's where you have to look. So let's take a look at all three of the possible sigma complex that result after the nitronium ion is installed in the ortho, the meta, or the para position. All right, so all we're seeing here, if you just zoom in here, is you're seeing ortho attack of the aromatic ring onto the nitronium ion. In the second one, you're seeing it occur at the meta position, and in the last one, it's at the para position. And then what the author of the textbook did is he took the time to draw all of the different resonance contributors. And you probably noticed that he highlighted two of them in green, and there must be something special about those. And there is something special about those. So if we look at the resonance structures, or sorry, I should say the sigma complexes that arise from ortho attack, you notice that we have the positive charge at the top, and then we have one here and one here, okay? The key one, the one that's highlighted in green, why is this one so important? Do you remember, was the methyl group, was that electron withdrawing or electron donating? Does anybody remember that? Heck yeah, absolutely, it's electron donating. So if it's donating electron density this way, is that going to stabilize or destabilize the carbocation? Absolutely, right? It's donating electron density to it, so it's going to stabilize that positive charge. Exactly. And so you see that we get two resonance forms in our sigma complex for ortho and para attack, where we end up with that positive charge adjacent to the methyl group. So it gets this extra stabilization. If you look at the sigma complexes that arise from meta attack, that never happens. Okay. And so that gives us the rationale, the explanation as to why the nitronium ion preferentially gets installed to form a nitro group on the ortho or the para positions. Give me a thumbs up if that makes some sense, because we're going to look at this same kind of closely related rationale a bunch of times. Cool. Awesome, awesome, awesome. All right, well, let's take a look here. If you're the kind of person who has to have some kind of reaction coordinate diagram to understand things, there's always a graph person in the class like, I need a graph, well, here you go. These are some beautiful graphs. And, you can think about it this way and say, well, not only is the sigma complex more stable, that results from ortho and para attack because you have that extra resonance form. The second thing would be the activation energies are a lot lower, right? This one, there's your activation energy. There it is here. And whoa, it's gigantic for meta attack, okay? So that's really just the rationale there. Nothing more than that, okay? So you can think about it as being a really high activation energy for the meta attack, stabilization for the ortho and para, and of course you get the extra sigma stability in the sigma complex. So it says here, ortho and para products predominate, very little meta product is formed. So explain that in terms of the sigma complexes. And the reason why you get more ortho than you do para, right, is because there's twice as many ortho groups as there are para groups, right? There's only one para group and there's two ortho groups. Now, however, there's one thing that you're going to want to throw stuff at me probably through the screen or something. This rule down here is an exception for toluene. Okay, and again, this is toluene. It's the only time that you get more ortho than para. If you replace the methyl group with the tert-butyl group, it's all going to go in the para because of sterics. Okay, so this rule, again, it's kind of an annoying one, but it's only true. This rule that they're putting down here at the bottom, it's only the statistical distribution is only a thing for toluene because the methyl group is so small. All right, and don't worry, if you're still not with me 100% on that, it's going to come up again. Okay, this isn't the last time you're going to hear about that. You guys want to look at another group? I do. What about a methoxy group? You guys remember this chestnut here, right? If you replace the methyl group with a methoxy group, okay, this is what we call anisole, okay? And anisole reacts much faster than toluene. This is 400 times more reactive than toluene. So toluene was 25 times more than benzene, and now you've got anisole, which is 400 times more than toluene. This thing is much more reactive. And you could probably guess why, right? If you have the oxygen attached directly to the ring, you can draw these resonance forms where you actually show lone pairs on the ring, right? And that renders the ring a good nucleophile, right? Because what's in a nucleophile is something that's going to donate electrons, right? So it renders it a really powerful nucleophile. So that's one of the reasons why it's so reactive, okay? And that's really the only reason you would need to know. So now the question becomes, we know that it reacts faster than toluene, faster than benzene. Well, what about the regioselectivity? When we have an anisole molecule and we try to do a substitution reaction, is it going to occur at the ortho position, the meta position, or the para position? Which one? All right, so let's take a look here. One thing before we get into that, though, that I always forget this slide. I don't know why, but I can never remember this slide. I even made a note about it before I came in here today. But anyhow, it says the methoxy group, as a matter of fact, it activates the ring so strongly that you don't even need a Lewis acid catalyst if you try to do bromination, for example, and you just get polysubstitution. So it would install at both ortho positions and the para position. However, note that for our class, okay, this is Chem 3101. We don't look at all, we don't start digging around in the weeds and all this stuff. We're just going to assume that you get monobromination only at the para position. So for this reaction, we would assume that you would only get this compound. And this is actually going to come up, I think, in our practice. Okay, so we assume that you get only this. All right. So now let's address that the whole regioselectivity idea. But before I get to that, really, this whole poly substitution thing, I mean, anything that's a really strong activator will do this, and a methoxy group is considered to be a pretty strong activator. Anyhow, I digress. Let's move over here and take a look at the regioselectivity. Look at this. It's in line with the methyl group in toluene in a way. In a way, yes, and in a way, no. If you look at where the nitration occurs, it occurs mostly at the ortho and para positions, almost no meta, but you see that the distribution between ortho and para is flipped now. It's mostly in the para position and very, very little in the ortho position. Okay? And if you're wondering, well, what's the rationale there? The rationale is sterics. Okay? The reason why is a methoxy group is so much bigger than a methyl group that it prevents the nitro group from going into that ortho position, or it limits it. And so most of the nitration would occur at the para position. Again, that whole ortho thing, that was just an exception for toluene, like I told you. So there you go. And if you're wondering, well, could we look at the sigma complexes that result from the ortho, meta, and para attack of the nitronium on anisole? The answer is sure, they're all here. And you notice again, same thing, that he highlighted two very specific resonance structures of the sigma complex. What do you notice about the ortho and para attack? You end up with an extra resonance form in both of them, right? Whether you do ortho or para attack, you end up with a fourth resonance form where you have the positive charge drawn on the oxygen atom, and you don't get that from meta attack. So again, let's back up. The reason why you get mostly para attack is based on sterics, okay? And the reason why we get para and ortho preferentially over meta is because when we have para and ortho attack, we get one extra resonance structure in our sigma complex. So that answers that. Again, for my graph person or graph people, here it is. Okay, if you look at the energy of activation for the meta attack, okay, here it is right here. Okay, this is our activation energy for meta attack. You see it's much higher than that for ortho and para attack, much, much higher, okay? And so we have a huge difference here, and that's why we're going to get the preferential, or the attack preferentially occurring in ortho or para positions. All right, deactivating groups. All right, the nitro group is an example of a deactivating group. So if you go back, let's just take a step back. If we go back here in 18.7, we talked about a methyl group, right, in toluene, and then we talked about a methoxy group. Both of those were activating groups. They were making the ring even more reactive than normal, right? More reactive than benzene. We saw that toluene and anisole were both more reactive than benzene. Now we're switching gears and we're going the opposite direction. Can we find a group that will make benzene less reactive? In one of those groups, a deactivating group, is a nitro group. So if you put a nitro group on your ring, if you make nitrobenzene, it's electron withdrawing, not electron donating. So since it's pulling electron density away from the ring, it renders the ring a really terrible nucleophile. You can see that just by induction, right? Nitrogen is more electronegative than carbon. Therefore, we have a dipole going away from the ring. Okay, so that's one way you could do it. But you could also draw a resonance form that shows the delocalization, right, of the pi electrons like this, where you show the electron density being drawn away from the ring in the resonance forms, right? You see that you have a positive charge here, here, and here on the ring when you draw all the possible resonance structures of nitrobenzene, and you should be able to do that. That's a question I could have asked you way back in chapter 2 of Organic Chemistry 1. And so if we look at the actual reaction rate, wrap your head around this one. Nitrobenzene undergoes nitration 100,000 times slower than the reaction of benzene towards the nitration. So you're probably sitting there thinking, well, this doesn't look very useful. You know, if it's that slow, you know, it probably isn't all that useful. And you might have to heat the reaction up more or put it under pressure or something like that. But now, what do you notice about the regioselectivity? It's completely changed, right? For an activating group, we saw that substitution occurred preferentially at ortho and para. Now what do you see? Where is it occurring? At the meta position. So now it's completely turned on its end. And you're probably wondering, well, does it have something to do with the sigma complex that results when you do the meta attack or the attack at the meta position? If that's your hunch, you're 100% correct. Take a look at the sigma complexes that result from ortho, meta, and para attack of the nitrobenzene on the nitronium ion. Well, what do you notice about the two structures that are highlighted in green? Do you notice that they have a positive charge on the ring adjacent to a nitrogen? Well, if you have a dipole going between this carbon and this nitrogen, what that does is it destabilized. Okay, and the same thing occurs here. So when we do ortho and para attack, we end up with this resonance form that is highly destabilized because we have an electron withdrawing group adjacent to a positive charge. That's bad, okay? That's very, very bad. But in meta attack, you look at all three of the sigma complexes, it never happens. It doesn't happen. We never see a positive charge adjacent to the nitrogen when we do a meta attack. So there you go. Give me a thumbs up. I know I've done a lot of talking. It takes a long time to get through these. Give me a thumbs up if you're with me on the rationale here. So electron donating group, ortho and para director, right? Based on the sigma complexes. Here we have a deactivating group. It's something that was withdrawing electrons. We get meta substitution, right? And again, it's based off of not really stabilizing effects, but destabilizing effects, right? And it's a much slower reaction. So again, for my graph people, here's the graph. Here it shows you that the energy of activation for the meta attack is lower than that for ortho and para. Why? Because in ortho and para, both of them end up with this goofy, or I shouldn't say goofy, this unstable sigma complex where you have the positive charge adjacent to an electron withdrawing group. There you have it, my friends. All righty. So with that, we're going to get into the halogens, but first I think we should take a short break because the halogens are an exception. They're deactivating because they're electron withdrawing, but what we're going to see is that even though they're electron withdrawing, deactivating, they're actually ortho and para directors, and there's a very good reason for that.